Today we are going to look at quantized conductances along edges, along quantum Hall edges. We already know that edges in the quantum Hall effect carry electrical conductance that's quantized. We also know that the same information about the quantization of the electrical conductance is encoded in the bulk. We know that because we can take a sample where the edges are what carries the current, and we can take a sample where the current flows in the bulk because it flows radially between edges, a Corbino geometry, and those two will give us the same quantization of the Hall conductivity, even though one encodes the quantization in the edges and the other one in the bulk. Now we'd like to, motivated by this amazing quantization of the electrical conductance, it makes sense to ask, are there any other quantized numbers in the edge or in the bulk of a quantum Hall system? And we're going to devote most or a large part of this video to another quantized conductance, a thermal conductance that is relevant to geometries that carry edges. So let's look at that. So let's look at this geometry, the one I just drew for you. And imagine a situation where either we put different chemical potentials on the two sides of the system, or we put two different temperatures on the two sides of the system. And let's ask, in the case of two different chemical potentials, what is the electrical current that's flowing? In the case of two different temperatures, what is the thermal current that's flowing? So let's start with two different chemical potentials. Zero temperature, for simplicity, it's not going to make much of a difference, as long as temperature is much lower than the chemical potential difference. But in any case, we look at zero temperature and calculate the current, the electrical current that's flowing. Of course, if the two chemical potentials are the same, there will be identical currents flowing on the two sides. But if they are not the same, there will be a net current flowing in one direction. So let's calculate that current. It's all those states which are between mu1 and mu2. They contribute a current. Each one carries a current that's the electric charge times the velocity. How many states are there of this type? Well, we need to integrate over all the energies from mu1 to mu2 multiplied by the density of states. But now comes a very crucial and fundamental observation. The velocity is just the derivative of the energy with respect to momentum. And the density of states is just 1 over the derivative of the energy with respect to momentum. Those two factors, density of states and velocity, cancel one another. This is a magic cancellation. Look what the consequences it has. The velocity and the density of states cancel one another. We are left with E over h multiplied by the difference between the two chemical potentials. H appears here from one of these expressions. So now if you want to express it in terms of the voltage difference, it becomes the familiar E squared over h times the voltage difference. That's the quantization of a single edge at nu equals 1. Now let's look at the thermal conductance. We now put two different temperatures, T2 and T1, and ask what is the thermal current, or what is the energy current that's flowing. Well, instead of each electron carrying its charge, now it carries its energy. They have the same letter, but by coincidence. Instead of little e, which is the charge, we have capital E, which is the energy. We have to multiply by the velocity because the thermal current is the energy times the velocity. And we need to integrate over the relevant energy range, so there will be a density of states factor. Now, density of states and velocity again cancel one another. Now, what replaces the mu1 and mu2 is the difference between the Fermi functions that correspond to temperature T1 and to temperature T2. And if T1 and T2 are very close to one another, we can just expand the Fermi function and write the derivative of the Fermi function with respect to temperature multiplied by the temperature difference. Now you carry out this integral, and what do you get? First of all, you see the same cancellation of velocities. So the outcome, the result, will be universal. Second, you see that the electric charge that you had here is replaced here by the temperature. Because while all electrons carry the same electric charge, here each electron carries a different energy, but the characteristic energy is the temperature. H appears here the same way it appears there. Temperature difference is T2 minus T1. This temperature here is the average temperature. And then there's a numerical factor pi squared over 3 that comes out of this integral. So thermal conductance is again quantized. It's quantized in a way that involves the temperature, but it's quantized and it has no dependence on non-universal factors. This is the integer quantum Hall state. This is the simplest of all. It's a single edge mode, non-interacting fermions. What happens if we go to the fractional quantum Hall effect? Well, again, the first thing we want to look at is the electrical conductance, and the second will be the thermal conductance. For the electrical conductance, in fact, for both of them, we're going to use the bosonized description of the edge, which we developed in an earlier video. And in that description, there's an Hamiltonian for the edge. It's a single edge, right? We generalize it to a multi-edge system, but we're not going to worry about that now. So it's a single edge, and it has the Hamiltonian has an integral over the density squared. This it's all given in terms of a bosonic field chi, and the derivative of chi with respect to position is the density. So this is just the integral of the density squared multiplied by some non-universal factor, v velocity divided by 2 sigma xy. And that's the Hamiltonian. And now the commutation relations of the canonical variables in the Hamiltonian are unique, are what makes this a special physical system. The commutation relations are the commutation of chi of x with its derivative is non-zero. It's a field that does not commute with its own derivative. The commutation is non-zero, and in fact it encodes sigma xy. It encodes the information about the type of fractional quantum Hall state that we're looking at. Now we'd like to use this to calculate the electrical conductance of the edge. So what we think of, there's this edge. We now change its chemical potential, and we ask, out of changing the chemical potential, how much current do we get? So the chemical potential is just the derivative of the Hamiltonian with respect to the density, and the density is proportional to dx of chi. So we take this derivative, and we find that the chemical potential is v over sigma xy times dx chi. Now so this is the chemical potential. So we change the chemical potential by introducing dx of chi, and now we'd like to see how much current we get out of that. And the way to do that is to use the charge conservation, to use the fact that rho dot plus the derivative of the current that we're looking at with respect to j is 0. Now you may remember from an earlier video that charge is not always conserved on the edge. When there's an electric field, charge is not conserved, but here we don't put an electric field, so nothing to worry about. Now rho dot is just proportional to the commutation relation of rho with the Hamiltonian, and that commutation relation will give us, or will lead us to see that the current is just the velocity times dx of chi, which is another way of saying it's the velocity times the density, which is more or less what we would expect. It's a chiral mode. So now if you just divide these two by one another, you find that the current and the chemical potential are proportional to one another, with the proportionality constant being sigma xy. So the electrical conductance of the edge knows about sigma xy. Surprisingly, and I'm giving you here a spoiler for the next slide, surprisingly, the thermal conductance doesn't depend on sigma xy, does not know about sigma xy. It will be just like this one, just like the electrical conductance, it will be universal. It will be independent of the velocity, but it will not depend on sigma xy. So let's see that happening and then talk about the implications of this. So the Hamiltonian is again the same Hamiltonian, the commutation relations are the same. But now it's a different situation. Now we're talking about thermal conductance, meaning we're not changing the chemical potential, we're not introducing new electrons to the system, we're just changing the temperature, meaning we're introducing more excitations in the system. Keeping the number of electrons constant, putting in more and more excitations. So we need to understand the nature of those excitations. To that end, we need to look at an equation of motion for this Hamiltonian. And the equation of motion, just take the commutation relation of the density with h, or even of chi itself with h. And you find that the excitation modes satisfy this equation. The time derivative of chi is the velocity times the x derivative of chi, which is again just chiral motion with the velocity v. And it has, therefore it has a dispersion relation, omega equals v times q. Now, that means that at any given temperature, there is an energy density, which is an integral over all the momenta, multiplied by the energy h bar vq, multiplied for each excitation mode. Those are bosonic excitations. They are basically particle Hall excitations. For each boson, for each excitation, the Bose-Einstein factor. Now, that's the energy density. But like everything, it moves chirally with the same velocity v. So the thermal current will be just this multiplied by v. So here's another factor of v relative to the energy density. You look at this integral and you find A, it does not have sigma xy. We lost it when we calculated the dispersion, and it canceled because of having sigma xy here and there. So it doesn't have sigma xy, but maybe more importantly, or equally importantly, it also does not have the velocity. Because you see here, v times q, v times q, v times q, you can absorb the velocity into q and change the variables to have an integral over energy. So the thermal conductance of a fractional quantum Hall edge does not depend on velocity, it's universal, and does not depend on the type of fractional quantum Hall edge that you're looking at. And if you have several edges, you'll just multiply the same, or you'll just add those edges as conductors in parallel, each conducting the thermal conductance of each of one edge, and that thermal conductance is independent of sigma xy or of the velocity. So there's a profound difference between charge electrical conductance and thermal electrical conductance when it comes to comparing between the integer and the fractional quantum Hall edges. Now there are several questions you can ask following this observation. First is, if the thermal conductance for nu equals 1 is the same as it is for nu equals 1/3, is there any state that will carry a different thermal conductance? The answer to that is yes. There are edges that carry a different thermal conductance, and one example to that, which is discussed in the chapter about topological superconductivity by Yuval, in the chapter about non-abelian states of matter, and even in the chapter about quantum Hall states, talking about the half-filled Landau level as a fractional quantum Hall state. When there are Majorana modes on the edge, their thermal conductance is a fraction, in fact, half of the thermal conductance of an integer quantum Hall state or a fractional quantum Hall state. And the reason for that is that Majorana fermions, in some sense, are half fermions, in the sense that this integral going from minus infinity to plus infinity should, for Majorana fermions, go only from 0 to infinity. So the thermal conductance is halved. More generally, fractional thermal conductance, whenever you have a thermal conductance that's a fraction of this pi squared over 3 in the units of T over H, whenever that happens, that's an indication for a non-abelian state of matter, and those will be discussed further on. There's another difference between electrical and charge conductance, and that involves the bulk. If you think now about this geometry, where you put a difference between chemical potential here and here, or between temperature here and here. Electrical current can flow in the bulk. Thermal current cannot, because the bulk is gapped. And therefore, the thermal conductance that we talked about in the context of the edge should be discussed in the context of the edge. The bulk doesn't carry this thermal conductance. It is gapped. It cannot carry thermal energy, at least as long as temperature is much smaller than the temperature of the gap. So to conclude, we looked at thermal and electrical conductance of edges. And I'd like to actually leave you with questions that are relevant but are not going to be discussed today. First is, what are the set of possible values for electrical and thermal conductances of edges? In particular, for thermal conductance, we saw mostly one value per edge, and I told you that you can halve this value. Can you get to other values which are not just a half of the fundamental value, but any other number? And are there also other quantized numbers that will characterize topological states of matter? Both of these questions are important, interesting, but I won't discuss them today. For today, we talked about electrical and thermal conductances on edges.